In this video, students should be able to c. Predict the possibility of precipitation of lightly soluble ionic compounds by comparing the values of ion product Q to Ksp. D. Define and explain the common ion effect. And E. Perform calculations related to common ion effect. 7.3c. Predicting the formation of a precipitate. Precipitate is an insoluble solid formed in and separates from the solution. A mixture of two solutions will produce a precipitate or not depending on the ion product Q present. Q has the same form as Ksp, but the concentrations of ions are taken at any given time. The solubility equilibrium equation for a slightly soluble salt, Ma, is as follows. If we have Ma, it will produce M plus equals and A minus equals. Note that the arrow used are reversible arrow to represent a slightly soluble salt. The Ksp for this salt is concentration M plus and concentration A minus. If we mix a solution containing M plus ions with one containing A minus ions, the ion product Q is given by Q equal concentration M plus concentration A minus. There are three possible situations. The first one, if the value of Q calculated is less than the value of Ksp. This means that the solution is not saturated. The solid will dissolve and no precipitate form. The second one is when the value of Q calculated is equal to the value of Ksp. This means that the saturated solution is formed and the system is in equilibrium. And the last one is when the value of Q calculated is greater than the value of Ksp. This means that the solution is supersaturated. Ions will form precipitate until the ionic concentration product of the system equals the Ksp. For example, will precipitate form when 50 ml 0.001 molar NaOH is added to 150 ml of 0.01 molar Mgcl2, given Ksp MgOH2 is 2 times 10 to the power of negative 11. The first hint you must note is the Ksp. The Ksp given for this question is 4 MgOH2. This means that when NaOH is added to MgCl2, the salt produced is MgOH2. So, the value of Q that we want to calculate is MgOH2. To solve this question, the first step is to calculate the number of moles of NaOH using the formula Mv divided by 1000. So, 50 times 0.001 divided by 1000 and we'll get 5 times 10 to the power of negative 5. The second step is to calculate the number of moles of MgCl2. 150 times 0.01 divided by 1000, and we get 1.5 times 10 to the power of negative 3. The third step is to calculate the total volume. So 50 plus 150 equal 200 milliliter or 0.2 liter. The next step is to calculate the new concentrations of NaOH and MgCl2. So we take the number of moles divided by the total volume. So we get the new concentration of NaOH equal to 2.5 times 10 to the power of negative 4, and for MgCl2 the new concentration is equal to 7.5 times 10 to the power of negative 3. The next step is to write the dissociation equation for both NaOH and MgCl2. First, we write for the NaOH first. Okay? So NaOH dissociate into Na plus and OH minus. If we draw ice table below that, we will write the initial concentration of NaOH is 2.5 times 10 to the power of negative 4, while Na plus and OH minus is 0. Since NaOH fully dissociate, the changes is minus 2.5 times 10 to the power of negative 4 for NaOH plus 2.5 times 10 to the power of negative 4 for Na plus and OH minus. At equilibrium, NaOH is 0, while for Na plus and OH minus, we will get 2.5 times 10 to the power of negative 4. Next, we do the same process for MgCl2. First, the dissociation equation. We will get Mg2 plus and 2Cl minus. Draw the ice table. The initial concentration for MgCl2 is 7.5 times 10 to the power of negative 3, while for Mg2 plus and Cl minus is 0. Since it fully dissociates, the changes will be minus 7.5 times 10 to the power of negative 3 for MgCl2, for Mg2 plus 7.5 times 10 to the power of negative 3, while for Cl minus, since we have 2 Cl minus, the changes will be 7.5 times 10 to the power of negative 3 times 2. So we get at equilibrium, MgCl2 will become 0, Mg2 plus 7.5 times 10 to the power of negative 3, and Cl minus will become 0.015. Then we take the salt that is given as a hint, which is MgOH2. We write the dissociation equations and it becomes Mg2 plus and 2OH minus. We draw the ice table and we substitute for initial Mg2 plus is 0, changes 7.5 times 10 to the power of negative 3 from MgCl2 and 2.5 times 10 to the power of negative 4 from NaOH. So, at equilibrium, the concentration of Mg2 plus is 7.5 times 10 to the power of negative 3 and 2.5 times 10 to the power of negative 4 for OH minus. Then, we write the expression of Q, which is concentration Mg2 plus times concentration OH minus to the power of 2. Substitute the value and we will get the value of Q is 4.67 times 10 to the power of negative 10. If we compare the value of Q and the value of KSP given in the questions, we will get Q is greater than KSP, solution is supersaturated, and precipitate will form. The same goes for the second example. Exactly 200 ml of 0.004 molar NgNO3 are added to 800 ml of 0.008 molar K2SO4. Will a precipitate form given the KSP for Ag2SO4 equal 1.4 times 10 to the power of negative 5. Okay, from this question, we know that the salt produced is Ag2SO4. So we do the first step, which is to calculate the number of moles of AgNO3 and K2SO4 using the formula MV divided by 1000. Then we calculate the total volume and the new concentration for AgNO3 and K2SO4. Then we proceed by using the dissociation equation of AgNO3 first, draw the ice table and put the value of initial concentrations, changes, and equilibrium concentration. We repeat the same process for K2SO4. Draw the ice table and put the values for initial concentration, change concentration, and at equilibrium. Followed by the last dissociation equation, which is for Ag2SO4 as given by the question for KSP. Rewrite the dissociation equations, so Ag plus and SO4 2 minus. Draw the ice table and we put the value of initial concentration as 0. And then for Ag plus, 8 times 10 to the power of negative 4 from AgNO3 and 6.4 times 10 to the power of negative 3 for SO4 2 minus from K2SO4. And at equilibrium, the concentration for Ag plus and SO4 2 minus is as shown in the video. Next, we write the expression of Q, which is concentration Ag plus to the power of 2 times concentration SO4 2 minus. Put the value in and we will get 4.096 times 10 to the power of negative 9, which is less than the value of Ksp given. This means that the solution is not saturated and precipitate will not form. Now, your turn to try to answer exercise 12. 7.3 D and E, common ion effect. Common ion is an ion that is common to two or more components in a mixture of an ionic solution, which means if we have a solution of ionic compounds, there is a possibility that there is common ion present in the solution. Common ion effect is the shift in equilibrium caused by the addition of a compound having an ion in common with the dissolved substance. Imagine we have a solution of Agcl. We add AgNO3 into the solution. If we look at the ion involved, we will notice that there is one common ion, which is Ag+. Consider that the silver chloride solution is a saturated solution. The dissociation equations can be written as Agcl produce Ag+ and Cl-. When AgNO3 is added, we will have common ion, which is Ag+. This will make the concentration of Ag2+ to increase. This means that we have a lot of Ag+ at the site of product. This will shift the equilibrium position to the left, which means to produce more Agcl. As an effect, the solubility of Agcl will decrease. In conclusion, the addition of a common ion will reduce the solubility of a slightly soluble salt. Secara ringkasnya, jika ada common ion di bahagian produk, ini menyebabkan concentration produk bertambah. Dan akhirnya, equilibrium akan shift ke arah reactant, ke arah kiri. So, ini menyebabkan reactants di bahagian kiri susah untuk jadi produk. Sebab produk dah banyak. Equilibrium akan shift semula, produk yang terhasil pulang balik jadi reactant. So, dia punya kesan adalah solubility of reactant tu akan berkurang. Dalam kes ni, solubility of salt tu akan berkurang. So, secara konklusinya, kalau kita tambah common ion, ia akan menyebabkan solubility of salt tu akan berkurang. Alright, for example, calculate the solubility of Agcl in liquid water. Okay, so kita let X be solubility of Agcl in liquid water. So, we write the dissociation equation for Agcl and draw the ice table. Put the value for initial as 0, at changes plus X, and at equilibrium as X. Write the Ksp, which is given 1.6 times 10 to the power of negative 10, and we will get X times X, and we will get X equal to 1.265 times 10 to the power of negative 5. Calculate the solubility of Agcl in 0.05 molar of silver nitrate solution. Okay, for question A, it is a common calculations like we do in 7.3a and b. But for these questions, we have common ion, which is Ag+, because we have AgCl and then we have AgNO3. To solve these questions, let Y be the solubility of AgCl in silver nitrate solution. As usual, we write the dissociation equation for AgNO3 to know how much Ag plus is added. So, from the dissociation equation, we have 0.05 molar silver nitrate. This means that we have 0.05 molar Ag plus. Okay, then we write the dissociation equation for AgCl, draw the ice table below, and put the initial concentration for Ag plus as 0.05 that we get from AgNO3. For Cl minus, it remains 0. Just Ag plus is different because we have the concentration of Ag plus from silver nitrate. For changes, 0.05 plus Y for Ag plus and plus Y for Cl minus. At equilibrium, 0.05 plus Y for Ag plus and Y for Cl minus. We write the KSP. Put the info 0.05 plus Y times Y equal to KSP. At this point, you should know that we can assume Y very small because the KSP is 1.6 times 10 to the power of negative 10. 10 to the power of negative 10 is very small, so we can use assumption. 0.05 plus Y is approximately 0.05. Okay, so we solve the unknown Y and we will get the solubility of AgCl as 3.2 times 10 to the power of negative 9. If you compare the solubility in question B and question A, you can see there is huge difference. The presence of common ion in question B has reduced the solubility of AgCl. Alright, and now it's your turn to try exercise 13. Thank you, class.